Hello and welcome, everybody. It is the top of the hour, so I'd like to get started. And without further ado, I'd like to welcome you to today's webinar, Homer's Approach to Economics. And I'm very glad that you could join us today. This webinar is unique and exciting because our CEO, Dr. Peter Lilienthal, will be able to join us to explain how economics play a role in the Homer Pro analysis. And just before we go further, I have some housekeeping items. We have you all muted, but if you have a question, enter it in this question box here, and we will get to that at the end of the webinar. We've set aside some time to answer your questions towards the end. Also, this webinar is being recorded, so in about a week, it'll be available for watching again, should you have any audio or visual problems. I'm Steffi Clowder. I'm the Associate Product Manager at Homer Energy, and I'd like to introduce you to today's speakers. First, we'll hear from Homer's CEO, Dr. Peter Lilienthal, who has a PhD from Stanford University in Engineering Economic Systems. And following his doctorate, he worked for 17 years at NREL as the senior economist with international programs. At NREL, he developed Homer optimization software, and he's since become an entrepreneur and founder of Homer Energy with our flagship product, Homer Pro. Dr. Lilienthal will start off by giving some background on why Homer takes the approach it does to its economic analysis. And then John Glassmeyer, Homer's Director of Energy Engineering, will jump in and do a demonstration within the Homer Pro software. And then at the end, we'll leave plenty of time to answer questions that are submitted through the question box. And quickly before we jump into things, I'd like to thank our partners in the industry. Now, without further explanation, I'll turn it over to Dr. Peter Lilienthal.
To pick the correct application to show. Hopefully you all can see my screen now that says Homer bridges different worlds. Give me a second here. Excuse me. So, thank you. So I created the Homer software as a bridge between some very different worlds. Not only do renewable advocates and diesel mechanics speak different languages, but you also have power engineers with very specialized engineering software that doesn't consider economics, and the financial community with their spreadsheets that don't consider technical constraints. Homer Pro is meant to fill that very large gap by having somewhat simplified treatments of all of these issues and serving as a communication tool between all these different perspectives. Projects don't get built unless all of these parties come together. At the most fundamental level, the simulation layer in Homer tells us what it costs to operate a system, how much fuel will it use, how much energy will be cycled through the batteries that determines how long they will last before needing to be replaced. The real heart of Homer is the optimization algorithm that tells us what system is best. But if you only do one system, but if you only do one optimization, you only know what system is best for one scenario. So sensitivity analysis tells us what happens if, for example, prices change or the load grows or the technology improves. How could that system design be adapted for different markets? And what do we mean by what system is best? By default, Homer finds the system with the lowest net present cost. But it must meet the load and reliability constraints. Net present cost is basically the same as total cost of ownership and gives very similar results to minimizing the levelized cost of energy. In order to do this, Homer must consider the capital costs that occur at the beginning of the project, the fuel and O&M costs that occur every year, and the replacement costs that only occur in certain years. There are other possible objective functions that you can use by resorting the optimization results, but we think these economic metrics allow us to best explore the design trade-offs. The most important trade-off is the one between capital and operating costs. Renewables have high capital cost and a low operating cost, and diesel generators have a low capital cost and a high operating cost. The discount rate is a single variable that compensates for what economists call the time value of money. In other words, a bird in hand is worth two in the bush, or $1 today is better than $1 tomorrow. The discount rate describes how much better $1 today is than $1 next year. It's very important to budget for replacement costs, especially since different components have different lifetimes, some of which, like the battery and generator, depend on how the simulation shows that they will be used. The fact that these costs don't occur every year and don't correspond to the project life creates several challenges to a consistent economic analysis. Frankly, the project life is a somewhat arbitrary concept. It's not as if the load will no longer need to be served after the end of the project life. And since HOMER is comparing many different system designs whose components will need replacing at different times, the arbitrariness of the project life can create some spurious results. Some systems may need to replace a component right before the end of this arbitrary project life, and others may not need to replace components until after the project life. The way we solve this potential problem is to amortize the component's replacement cost over its lifetime. In effect, this is as if you took out a mortgage for that component and its mortgage was paid off at exactly the time that you needed to replace it, and then you took out another identical mortgage. In this way, the annualized costs remain constant. We also have to have a salvage value so as not to inappropriately disadvantage systems where a component needs replacing right at the end of this arbitrary project life. One of the best ways to understand what a model does is to understand what it doesn't do. For example, HOMER only considers the cost of meeting the load and with the exception of sales to the grid, it doesn't consider revenues. This is why we minimize net present cost instead of maximizing net present value. HOMER is not a financial model for a utility business that can calculate enterprise profits. Rather, it is an economic model of an investment in a project. And unlike financial models, economic models don't consider transfer payments such as taxes and depreciation schedules. HOMER is used in 193 countries, each of which has a different tax structure. HOMER can also use any currency, but everything has to be in the same currency. So we avoid dealing with currency conversions, capital controls, and the difference between official and unofficial conversion rates. We also don't consider capital structures such as the terms of different debt instruments, whether there are concessionary terms such as grace periods, and the split between debt and equity returns. We work with a lot of developers and financial organizations, all of whom have their own spreadsheets with their own way of handling these issues. Frankly, these issues are always being tweaked and are better handled in spreadsheets, which are easy to tweak, whereas spreadsheets are really incapable of the amount of computation HOMER performs in its simulations and optimizations. HOMER will output the data that these financial spreadsheets need, and we can create macros, and we can help you create these macros and templates in your financial spreadsheet to automate the transfer of HOMER's output data into those spreadsheets. And with that, I'll turn it over to John.
All right, thank you, Peter and Steffi. So I'm going to demonstrate in the HOMER Pro software some of the things that Peter told you about. Now, when you open HOMER Pro, it typically starts here on the home page. One thing I'll note is that for this demo, I'm using a beta version of HOMER Pro, version 3.10. Now, many of you will likely be using the current release version 3.9.2. And this beta does include some nice cool new features, but it'll look pretty similar to the release version that most of you are likely using. Now, to demonstrate some of the economics that Peter introduced, I'm going to use one of the sample files that ships with every copy of Homer Pro. You can access these sample files here under the File menu under Open Samples. And Homer Pro ships with over 20 of these sample models that can demonstrate interesting analyses that span the various markets that people use Homer Pro. So for this particular demonstration, I'm going to use this file right here, this African mini grid file. It represents a really basic design for mini grids, and I've arbitrarily chosen to use it because it's a really simple system that you can model with Homer Pro. I could have just as easily used a model that represents, say, a grid connected system or even a different remote application. So I'll go ahead and open that. Okay, and now that it's loaded, you'll see it starts here on the home page. And here you can set the project location as well as it includes some of the key inputs that we've pulled from elsewhere in the model that we think are particularly important, such as the discount rate, the inflation rate, and the project lifetime. Now, this particular sample file uses different currency. So to see that, I'm going to go to the project ribbon and click on the economics button. And here you can see that you can select just about any currency you like. Here, this model is set to use the Nigerian naira. And a Homer model can use pretty much any currency as long as you use the same currency across the entire model. In this tab, you'll also see that we've got that nominal discount rate and inflation rate. And together, these two numbers Homer uses to calculate the real discount rate. I like to think of the real discount rate as the interest rate that you'd see after you've pulled inflation out. We also here under the economics input, you can set the project lifetime, as well as we've included a system fixed capital cost of 450,000 naira. This system fixed capital and O&M cost inputs, these are great spots to put inputs that you don't expect to change with the hybrid generation design that Homer's recommending. So for example, here, this 450,000 naira might represent, say, the transmission and distribution system or some of the pre-engineering that you'll need to do for this particular project. So you'll also see in this model that we're performing a sensitivity analysis here on the discount rate. So we've got a range of potential nominal discount rates from 8% up to 14%. One thing that you may know is that in less risky investments, you tend to have a lower interest rate and a higher one if you think an investment is more risky. Interest rates or discount rates also tend to be higher for remote areas and places where they have trouble accessing capital. Some factors that people often use in the interest rate are the rate at which they can get a bank loan or the weighted average cost of capital, sometimes called the WACC. But in simple terms, this is really the factor that determines how Homer views investment today versus those in the future. Now, let's take a look at some of the results from this model. But before I do that, let me introduce some of the technologies we're considering. We're going to be modeling the option of up to 2 generators, Gen A and Gen B, a solar photovoltaic PV component, a battery converter, and then a storage component that we're modeling a lithium-ion battery. So I'm going to click the results so that we can talk through what are some of the results that you might expect to see from this model. So if your model contains sensitivity variables, like this one does, the first thing you'll notice is here in the sensitivity case table, there will be a number of entries. For each of the sensitivity cases in this table, Homer will display the lowest cost design. That is, each of these systems have the lowest net present cost after comparing all the various design options. So, for example, here for the case with an 8% discount rate and a 100 Naira per liter diesel fuel price, you can see that the lowest cost design we found had 92.3 kilowatts of PV, two 60 kilowatt gensets, 34 of these lithium ion batteries. They're sized to be roughly 1 kilowatt hour of nominal capacity, and a 37.5 kilowatt converter. If I click on this system in this table, it changes the table below. So in this table below, the optimization results table updates to show how all of the systems that we simulated, all the different design options here on these sizes, perform at that selected sensitivity case. That is at 8% nominal interest rate and that 100 Naira per liter diesel price. And again, you'll notice that the lowest net present cost, the lowest cost system, is here at the top. It's all ranked according to the net present cost. And this top system, this overall winner, is the same system that is shown in the table above at that sensitivity case. HOMER always does that. It takes this overall winner and puts it up here. So you will also see that this overall winner at this sensitivity case, it costs 51.7 million Naira to install. And on average, it costs about 11 million Naira to operate each year. Now, the operating cost may vary from year to year, but this is the average operating cost. And together, this initial capital cost and this annualized operating cost can be used to calculate this net present cost that we use to compare systems. So let's take a deeper dive. I will double click on this system from the optimization results table, the overall winner hybrid system, to review some more detailed results about it. So when you do that and you open up the simulation results, you start here on the cost summary page. Let me expand this out a little bit so we get everything on one line. There. So now the cost summary page has a detailed breakdown of the cost categories that went into determining those summary costs that we saw in those two summary tables. So if you want to look at that, you can see, for example, that there's the net present cost here. The system total net present cost is 194 million Naira. It also has a detailed breakdown of the cost categories. So for example, you might see that each of these gensets, genset A and genset B, cost about 4.9 million Naira to install. And for genset A, you can see that you spend about 27 million in present day dollars replacing it, $15 million maintaining it, operating and maintaining it, and almost 90 million Naira on fuel. You'll also notice that based on these costs, you're probably using genset A a lot more than genset B. One thing that you can do, if you click this radio button here, you can see these costs spread out, that is annualized or amortized across each year of the project. And this lets you, I like to look at these cost summaries this way because it lets you see, what's the per year impact in each of these categories or in each of these components. Now the cash flow tab, it presents the same data, but it's shown in a year-by-year format. So you can see, for example, the initial purchase here in year 0, and then the various items you buy each year thereafter. So for example, in year 1, we spent 7.2 million on fuel. Here in year 3, we did a replacement of some piece of equipment and spent, again, that same amount on fuel. If you click here on the cash flow and change it to the discounted version, it'll present that same data, but it'll apply that real discount rate that you specified. And you'll notice that when I did that, it affected the overall costs such that these costs presented in this cash table are now in present day dollars, that is today's currency. If you were to add up all of these columns, you would get the net present cost that HOMER uses to determine how much a simulation costs and that it uses for comparing against other simulations. You could also look at these by component. So you can see that there's a replacement here. You might wonder what's being replaced. you can see that it's all part of that Genset A cost. So that's likely a replacement for not only buying fuel for Genset A, but also replacing it. And if we look out, say, to year 10, you can see that there's, let's put this back on cost type, replacement out here in year 10, that's likely includes a battery replacement. Okay, so Homer Pro comes with some great tools for visualizing your findings. You know, you look here and you can see how much fuel I'm using, the performance of individual technologies such as the gensets, the batteries, or the PV. There's a lot of technical constraints that go into determining those economics. I'd also give you some insight into the emissions. But you know, the real story is the real story is how you use the economic inputs to affect the design you choose. So here, let me close this more detailed summary. Let's take a step back and talk about some of the visualization tools for comparing options. So one great graphical tool that comes with Homer Pro, and I'm going to put this in the graphical tool to show you, is our optimal system type, or OST charts. Now this chart allows you to see how the optimal design, that is the overall winner, as I pointed out earlier, how that overall winner or optimal design changes as various sensitivity inputs change. So this OST shows how the available price of fuel, ranging from about 70 Naira per liter up to 130 Naira per liter, and the discount rate, the nominal discount rate, which ranges here, again, that 8% to 14%, shows how it affects the design you might choose. So these colors represent two potential designs. The orange is a low-cost design that includes both generators, some solar PV, and some batteries. And the blue, down here in the lower right, that is at low fuel price and high discount rate, includes the generators and the batteries. So the real distinction between these two colors is whether or not it contains solar photovoltaics. So looking at this, you can see, and some of this may be intuitive to you, but it gives you some quantitative backing that at higher fuel prices, the relatively higher cost of diesel generator encourages the use of renewables. Also, this shows that areas that have good access to capital and hence lower interest rates are also encouraged to use renewables due to their higher initial cost but lower operating costs. So as you can get a better discount rate, you'll be more likely to use renewables because of their high cost and low operational cost. Now, let's switch back to the tabular view because I'd like to talk a little bit more about how Homer helps not only with finding the low cost system, but with doing an investment analysis. So building upon this deeper understanding of Homer's net present costs, what it means and how it handles project and component lifetimes, let's talk about how Homer can determine the payback and internal rate of return. So Homer performs this by comparing a particular simulation to another base simulation. And the way to calculate this is to click on this button, the Compare Economics button. Once you click this button, Homer will ask you to select your base case. And you know, another term for this base case, sometimes it's called the business as usual case. It's the case, the system that you might design if you weren't doing an incremental investment in renewables or storage. And you can see that Homer's made a guess about what it thinks your base case will be. It's done that based on which of these systems has, if I scroll over a little bit, the lowest initial capital cost. And it has guessed that we want to do the 100% diesel case. And I would say this is commonly what people, since it's the traditional way of supplying power in remote areas, this is commonly the base case that you would select. If this were a grid connected system, you might say, select a system that is the grid only option. So anyway, here I will agree with Homer and choose the system that it guessed for me. Now, once I click OK, Homer will calculate the payback for all of the systems within each sensitivity case. There, it finished. So here in this 8% nominal interest rate and 100 Naira per liter diesel fuel price sensitivity case, Homer has calculated the simple payback as 8.5 years and calculated an internal rate of return of 11%. And you can see these values calculated for other systems as well. It's interesting to note that the lowest cost investment may not be the one with the best return. So for example, here you can see that we've spent less money and did not invest in PV, but it gets a faster return on this initial capital. So you put in a little bit less money and maybe get a little bit, a little different operational savings, but you'll recoup that investment relative to the diesel only case faster than if you did this fully optimal low cost design. In effect, you're getting a faster return on your money, but you're leaving some cost savings on the table. So if you'd like to get more detail about how Homer determined these payback, ROI, and IRR values, you can, again, double click on a system to open up those detailed simulation results. And there's a tab focused on this compare economics called the Compare Economics tab. And here you can see some additional calculations, such as the present worth of your investment, the annual worth of your investment relative to that diesel base case, as well as the return on investment ROI, and some different ways of calculating paybacks and IRRs. You can also see these graphically by clicking on this charts button. And here, this charts button shows on top the hybrid design, the design we selected. So you can see you've got a large capital outlay and then relatively modest operational costs, as compared to the diesel system where you have a relatively smaller capital outlay, but significantly higher operational costs. And if you click on this cumulative radio button here, I like the way this displays because it shows that diesel system with its initial capital outlay, and then you can see that every year you're spending money, and that's driving the costs, showing how much money you're spending, as contrasted to that current system, that overall winner that we chose to look in more detail at. It's got that larger capital outlay, but each year you're not spending as much money, and eventually, at least in terms of simple payback, they cross over. So they would cross over in, if we look down here at our simple payback, 8.5 years. If you draw a line down here, that's about 8.5 years. If you wanted to see the payback after reflecting on the, including the fact that these cash flows are discounted, with that 8% nominal discount rate, you can see that these get a little bit, they get concave upwards, and it pushes out that payback. And this 12.5 year, roughly, let's see what Homer's 12.34 years is when those discounted cash flows cross over. So this would pay back, if you wanted to account for the discount rate, in about 12.3 years. So with that, you can see that there's a lot of different ways for looking at the economics of systems and choosing what you might want to invest in. And Homer, by providing you a lot of these detailed graphical and quantitative outputs, gives you the decision tools necessary to make a smart decision and a smart investment. So with that, I'd like to pass it back to Steffi to select and moderate some questions. Thank you.
Thank you, John. That was great. And we have had questions coming in the whole time. If you do have any more questions or think of any as we go, don't be shy and just type them into the questions box. And I think a great one to start with is, what is the difference between NPC and NPV? John or Peter, do you want to start answering the questions?
Yeah, I'm happy to take that. So NPV, net present value, is sort of, the classic term that's used in literature and in business schools, et cetera, where you have both costs and revenues, and you're trying to maximize profits, and you want to maximize the net present value of the revenues minus the cost. But since we don't really look at revenues, we're really trying to minimize the cost of serving the load. We decided not to use the term NPV, frankly, because what we would be doing is minimizing a negative number in a sense. So we call it net present cost. It's really the same concept, but but it's focused just on minimizing cost.
Okay, great.
I'd like to just add one thing to that that's interesting. You know, net present cost really is a Homer specific term. If you Google it, it'll often come up with, you'll find really high in the rankings Homer Energy mentioned. So it's something that we used, and it's because it's such a unique way of doing it, it gives you really powerful answers.
Right. One of the reasons we wanted to have this webinar is because there are a few things in Homer that we do a little differently, and we tried to explain why we do it that way, such as the way we handle replacement costs in relationship to the component lifetime.
Thank you, guys. And related to the NPC, there was a question about how does Homer take into account asset depreciation as it calculates the NPC?
Okay, so depreciation actually can mean two different things. So especially now, I'm not familiar with the tax code in every country, but in the U.S. we have a complicated tax code, and depreciation schedules are a part of the tax code, and that's for financial analysis. But depreciation can also just mean physically, equipment wears out over time and it depreciates. It wears out, it becomes less valuable, and so that's what we talk about when we talk about amortizing the replacement costs over time. In effect, it's sort of like straight line depreciation every year. So if the component is gonna last 10 years, we sort of debit the project with 1/10 of the replacement cost every year, and for the 10 years, at the end of 10 years, it's fully depreciated in a physical sense, needs to be replaced. And so we simulate the purchase of a new component and start that process all over again.
Thanks, Peter. And John, I think this one might be good for you just because you have the context of within Homer Pro. How do you simulate or optimize based on the lowest LCOE or the lowest capital cost in the case that you don't want to optimize on net present cost?
So, you know, we specifically chose net present cost because it factors in both the capital and the operational costs. You know, you can optimize on other variables such as, but it can sometimes lead to less interesting results. For example, if you chose to optimize on lowest capital cost, that would likely bias you towards doing a diesel generator system. And if you look at the net present cost comparison of that, I'd say you're leaving money on the table because you're going to have to spend more to operate it, even though it has the lowest cost up front. And I think you specifically mentioned the LCOE. Most of the time in Homer Pro, the LCOE and the NPC are the same. But LCOE is a bit of a flawed metric because it is normalized by the kilowatt hours. And particularly in certain systems, you are delivering different kilowatt hours, but providing the same energy service. Anyway, this is a classic critique that, you know, particularly energy efficiency advocates would have about, you know, saying that a kilowatt hour is a kilowatt hour. So anyway, that's part of the reason we use net present cost. One other thing I'd like to add about this is that just because Homer uses net present cost to determine the optimal system, you can, for example, I guess I'm not showing my screen or I demonstrate it, but you can click on a column and resort on a different column. So if you wanted to, say, find systems that generate a reasonable NPC, and then within that set of systems, minimize the capital cost for those that meet some criteria, you can definitely do that with HOMER Pro. And there's a lot of tools in the user interface for sorting and filtering results so that you can apply additional criteria such as or hurdle IRR or other common criteria for selecting an investment.
Thanks, John. And I think something that would be good for you, Peter, would be, can you please explain once more what salvage value is?
Sure. And we get this question a lot because it's an artifact that we put in there to avoid, I can call them discontinuities or spurious results or whatever. But so imagine two systems, and they're very, very similar. But one of them, but they're not identical. When one of them has to replace a component right before the this project life is over, and the other one, no, that component is still good, but it's going to need to be replaced shortly after the project life is over. So these projects are really, really similar, but one of them is going to incur a very big cost that the other one's not going to incur. We have to adjust for that because that you're not comparing those two systems fairly. Because one of the systems gets to the end of its project life and it's got an almost new component, and the other one gets to the end of its project life and it has a very old component. So when we talk about salvage value, we're not expecting people to actually remove that component and sell it as a secondhand component on the market. We're just trying to correct for this problem that occurs because you have this project life, which is really an artificial construct. It's just that you can't calculate net present cost without it. So and everybody likes to think about, do their analysis for a project life, but it's kind of it's like I said before, it's kind of an artificial construct. So we're not expecting people to actually salvage these components. We get that question all the time, that we're not going to salvage this component. Why is there a salvage value? But if without the salvage value, we're going to really disadvantage certain projects sort of inappropriately based on the timing of their replacements. So it's just a way to correct for that so that you don't get sort of spurious results. We want to treat all the systems consistently, and that's how to correct for that.
And I'd like to contextualize that in terms of that hybrid system that we spent a lot of time looking at through the demo. You'll notice that contained not just PV, but also 2 generators, as well as a battery, as well as a converter. And you would expect each of those pieces of equipment to vary in terms of their useful life. And so the fact that we're bringing all these together in a combined hybrid generation system means that it's really important to figure out a way to balance the different component lifetimes and true them up for that project lifetime that Peter was talking about.
Thanks, John. And the next question we have is, what is the difference between LCOE and COE?
There's not necessarily a difference. COE is maybe not that well defined. It's cost of electricity versus the levelized cost of energy, but it's this. The important question here is, what does it mean to levelize something? So you've got inflation, you've got these replacement costs that come at different times. So levelized cost of energy is a single number that encapsulates the cost of energy over the whole project lifetime. And the way we calculate it is, we take when we calculate annualized costs, we're saying this annualized cost, if we incurred it for every year over the project life, that would have the same net present cost as the actual cash flows, which vary. So we take that annualized cost and we divide it by the quantity of energy served, and that's your levelized cost of energy. So it's a number that wouldn't change over the project life.
And just to add to that, in terms of the when we talk about COE as an output from a HOMER simulation, that is the cost of energy, meaning the cost of reliably serving the load that we specified, subject to those loads requirements. You can also do, a levelized cost of energy generally is just a way of spreading out some money that goes in to get some energy out. So for example, we have this system cost of energy. Oftentimes you'll see when you look at analyses of individual distributed generation such as solar PV, there might be a different cost of energy for that energy coming out of the PV, and those may not be, the kilowatt hours coming out of those may not be equivalent. They may, the PV may provide power when you don't need it. But with a HOMER analysis, the cost of energy that we're coming back with is the fully burdened cost of energy to supply that particular load that you've specified.
Well, another clarification, actually, in some of our tables, we use COE instead of LSCOE just because it fits the column better. It's just shorter, and so we treat it sort of synonymously.
Thank you, Peter.
Steffi, if I could jump in, I'm just looking at the questions, and there's one that I think is really important. I just want to jump in and answer it.
Sure.
So I'll just read the question. It says, say when we want to input the capital cost of PV, should we input the price of PV? Whoa, sorry, somebody's adding questions and it moved it. Sorry. Should we input the price of PV only, or should we input the total cost for the PV installation as well? PV mounting, the mounting hardware, the installation cost, the cabling, balance of plant, etc. That's a very important question, and there's probably a lot of questions like that we didn't answer because, frankly, HOMER is an economic model. Pretty much everything about HOMER has economic implications. But I do want to address this one because it's very important. All of the costs of the project have to be accounted for in HOMER somewhere. So, when we talk about the cost of PV, we are talking about the total installed cost. And it should include all of that stuff like shipping, mounting, labor, any sort of import tariffs or anything like that, dealer profit, the wires, the mounting hardware, and the foundations. It's the total installed cost of that component. Now, where it takes a little thought is a lot of times you'll see people quote the cost of a PV in there, or batteries for that matter, and they're including the inverter in the cost of the PV or the batteries. Well, we have a separate component for the inverter, so you don't want to double count either. You've got to allocate your costs carefully and fully, but with no double counting. So then, for example, if there's costs that like the distribution system or the building and it's going to be the same building or the same distribution system, no matter what this power system is, then that goes in the system fixed cost. John showed that right at the beginning of his talk. So all of the costs have to be somewhere. You have to be careful not to double count any of the costs, and you have to put the costs in the component. So like if the PV system is twice as big, it should have twice, the cost should be twice as much, because HOMER's gonna look at different sizes. One thing we didn't show was how you can have economies of scale. So like a PV array that's twice as big doesn't need to be twice as expensive. We probably should have shown that, I apologize. That's in our cost table. But it's super important to allocate all the costs somewhere without any double counting, and those should be total installed costs.
And actually, I want to jump in here because I see a somewhat related question, and it asks, what is the O&M cost per year for PV? So one of the things that that HOMER Pro includes is throughout the model, we provide generic components, and those provide starting points for these costs. Now, I want to caution about using those, because what those let you do is they let you give you a rough feel, an order of magnitude, if you will, of what a cost should be. What, in terms of an individual project, you would expect the cost to be either higher or lower, depending on factors such as how remote is the project, what's the tax situation, is it going to be taxed, is it hard to access, is there labor available, what are labor costs? There's a lot of factors that get rolled up. Peter alluded to a lot of them. So there's, when you're trying to figure out, you can use Homer Pro as a starting point for understanding some of the input costs. Those come included with a lot of our generic costs, but they will need to be trued up for each individual project.
Thanks, John. I also see a question. Does Homer allow risk-based probability on interruption of diesel fuel supply or significant variation in the delivery cost of diesel fuel? I think that's a really interesting one.
Well, you can do a sensitivity on the cost of diesel fuel. And we almost always do that because it's quite uncertain. And it has a huge impact on the system design and the economics of the project. The interruption in the supply of diesel fuel is a little tricky. I'm not, no, we don't do that. We do, if you're modeling the grid, can model the outages on the grid, either scheduled outages or random outages. Fuel supply, hopefully you've got enough storage you should just increase the size of your storage, I guess.
I mean, one option there is that it's a really easy output to get out of Homer Pro is to look at the 100% renewable case and see, well, what's the bookend to how many renewables would I need to go on indefinitely without diesel?
Well, yeah.
What you'll find if you do that analysis is that the capital cost for those sorts of designs tends to be significantly higher than a hybrid design. And you may have a lot of PV and a lot of batteries in a solar battery type configuration that you'd want to see, at least gives you the input to see, is that something I'd like to consider? And it's really easy to get those using Homer's optimizer.
This might be a good opportunity to describe one of my favorite metaphors, because models are inherently a simplification. They have to be a simplification. And the best way to illustrate, and so there's details like that. There's always going to be details that a model can't do. And the best way to think about that is imagine a map. A map is a model of the world, and it's a simplification of the world. And if it weren't, if your map had all of the detail of the real world, it would be as large as the real world, and it would be useless. So the whole value of models is that they're simplifications. And depending on what problem you're trying to solve, you might want different kinds of simplifications. So Homer doesn't do everything. And if it tried to do everything, you wouldn't be able to use it.
Thanks, Peter. I see a couple different questions that are circling around the same concept, asking if there's a way to escalate the fuel costs or the grid power price over the project lifetime, or if you can escalate how the grid or how the load increases over the project lifetime. Can Homer do that?
And so I'll take that one. I believe since Homer 3.6, 3.6 or 3.7, I think, we introduced a feature called multi-year. And the multi-year feature allows you to do perform changes in costs and changes in performance of the various components and fuels that are in your model. So you can definitely do that sort of escalation. By default, we assume that everything escalates according to the inflation that you assume. That's implicit in doing a real discount rate analysis. But by having that multi-year, it helps you to see what the impact of a different escalation schedule for, say, the diesel fuel is. And one interesting implication of how you do that, say if you did a sensitivity on the load, you expect load growth, that will have implications not only in the overall economics, but you would actually change how you dispatch your system. You change how you use the components as the load grows. And Homer supports that when you do a multi-year analysis. So it's a really powerful tool. If you do use it, the one trade-off to it is that you have to do a lot more calculations, so it takes a little bit longer. But a lot of our customers really like it. They find that it helps them see, well, what are the impacts of all these changing factors? It gives them a way to look at that.
Yeah, if you assume everything escalates at the inflation rate, you can just do a 1-year analysis. Simplifies things a lot. But if you want to have differential escalation rates for different things like fuel prices, or you want to do load growth, then we have this new multi-year feature.
Great. Thank you guys. I think we have at least captured about half the questions, but thank you for so many questions. I think we'll wrap things up here. If you didn't get your question answered, there are several resources at your disposal. We have our full help manual online, as well as knowledge-based articles that we've written up over the years on commonly asked questions, or there's a user forum where users answer each other's questions. And each of these can be queried through the search bar on homerenergy.com. So that is where I would start if you ever had a HOMER question for us. Otherwise, our support team is always available for you. And thank you very much for attending the webinar. I hope that you've learned something, and the recording of this webinar will be made available in about a week, and we will keep you posted on that. Otherwise, I hope to see you at our conference or at our next webinar. Thank you very much for your time.
Bye.
Bye.